The 2-unit part of motion, really simple. This is always with respect to time and usually just moving in one direction. Extension 1, we extended that a little bit, where we looked at 2 dimensions, projectile motion, but also a specific type of motion, simple harmonic motion. Extension 2, we go a little bit deeper again into dynamics. So dynamics, good old Newton, what we would do without him, eh? Newton's law, there's the first law, I'm sure you know it well. Corpus omni persevere in status duo quiescendi vel movendi. I'll translate it, okay? Oh, there we go. So, basically, I would say everybody continues in a state of rest or of uniform motion in a right line, that just means straight, unless it's compelled to change by some force. Okay? So force is the key thing, and that's what we're going to be investigating when we look at it from an extension 2 point of view. If you're moving, you can't stop unless a force is impressed upon you. Okay. That's basically the first one. So the second one, I've been telling you motus proportionalium. That's the one that most people know. It's basically saying the change of motion is proportional to the motive force. In other words, the motive force proportional to change in motion, well, change in motion, change in velocity is acceleration. So force is proportional to the acceleration. So some constant times acceleration, and as someone very famous, that good old Newton, worked out, well, that constant is in fact the mass. Force is equal to mass times acceleration. And then the third law, actione contrarium. Okay. Often quoted as to every action there's an equal and opposite reaction, but what it actually is this. To every action there's always opposed an equal reaction, or the mutual actions of 2 bodies upon each other are always equal and directed in contrary parts. And that's kind of talking about some forces that are acting out there that you don't necessarily realise. It's like, I'm just standing here right now, and you'd think, oh, well, there's no forces at all, but there is, because of course gravity is constant, gravity is there. Now, why aren't I going through the floor, or why aren't my knees buckling? Well, that's because there's an opposed force. So whilst I'm applying a force to the ground, thanks to gravity, the ground is also applying a force to me, which balances and is equal, and hence I don't fall down. That's the basic idea. There's the 3 laws that we'll be using for our problems. Okay, so let's look at this thing, acceleration. We've seen it can be the second derivative with respect to time. We've also seen first derivative of velocity with respect to time as well. That's useful when acceleration is a function of t, or function of time. When it was a function of x, we used d dx of a half v squared. But often more useful is v to v dx, which allows us to separate the variables out and do our integration. So here's an extremely old question, 1981. So we're going to assume the Earth is a sphere, radius capital R, that any point little r, which is bigger than capital R, from the centre of the Earth, the acceleration due to gravity is proportional to 1 on little r squared and directed towards the Earth's centre. We're going to project a body vertically upwards from the surface of the Earth, and its initial speed is going to be capital V. We're going to prove that our object will escape the Earth if and only if capital V is greater than or equal to the square root of 2gr. Now I know how you love drawing diagrams, so it's a good idea to draw a force diagram with these so you get a feel for what the question's doing. The blue circle represents the Earth, and here's the path that I'm going to travel on. Now what do I know? There's my particle, good old Bob we'll call him. At the Earth's surface, little r is equal to capital R, that was the radius of the Earth. Initial velocity was capital V. The acceleration at the Earth's surface is minus g. At some point it will stop, or if it does stop, that'll be when velocity is equal to 0. Okay, the forces. So We're sending our particle up. What are all the forces acting on it? Well, gravity is an acceleration. Weight. Okay. So how do we set this up? We define which direction is going to be positive. I'm defining that to be up. And that's what we call our resultant force. So the resultant force is all of the forces acting together. And basically, I just need to define the positive direction. So that force that I've actually drawn in there is not a force acting on the particle. It's just the result of all the forces. Okay? So I'll use a different colour for the forces acting on the particle. I'll use the red ones. And as we said, the force due to gravity, which is also called weight, mass times acceleration, they told us acceleration was proportional to 1 on r squared. So I'm saying it's equal to a constant. That constant, I've used the Greek letter.
Micro.
Anyone know what that Greek letter is?
Micro.
Alpha.
Yeah, some of you picked it up. I gave you a huge hint. It's mu. mu. So it's m times mu over r squared. So from there, I can come up with an equation, my force equation. My resultant force, mr double dot, is equal to all of the forces acting on this particle. Well, there's only one. And the only one acting on it is this m mu on r squared, and it's in the negative direction. So I've made it negative. Now I can divide through by the masses here, and I've got an acceleration equation. It's acceleration in terms of displacement. Okay, we're using r instead of x, but it doesn't matter. It's just a pronumeral. Now we know that when little r is equal to capital R, the acceleration is minus g. So I can actually go and work out what that constant mu is equal to. So subbing in, and we get mu is gr squared. So minus gr squared on little r squared is my acceleration formula. Okay. So I'll use v to v d, well, x, but in this case it's r. So v to v dr. Let's separate those variables out. Now we knew that at the Earth's surface, so that's when the displacement was capital R, the velocity was capital V. I'm going to come up with a link between velocity and displacement. So integrate v, yes I get a half v squared, but like I did yesterday, instead of writing it as a half v squared, I've multiplied the other side by 2. I suppose it's just fractions, it doesn't really matter I suppose. Subbing in, let's play around with it, so there we go. V squared is that wonderful expression that we have there. So I've got an expression. Now, the question says it escapes the Earth's atmosphere. So, if it escapes the Earth's atmosphere, it never stops. Because if it stopped, then it would come back down, and it hasn't escaped the atmosphere. So, our radius, or our displacement, I should say, I saw R there, just thought radius. Our displacement is, if you like, approaching infinity. It's going to keep going, and never stop. So I want to find the limit as R approaches infinity. And we get this capital V squared minus 2gr. Now, the other thing I know is that V squared is always greater than or equal to 0. So V squared minus 2gr must be greater than or equal to 0. Giving me that the V squared, the initial velocity, must always be greater than or equal to 2gr. Hence, that's my escape velocity. Yes, I could go faster than that, but the minimum to escape would be 2gr, or V squared would be 2gr. So if V is greater than or equal to the square root of 2gr, the particle will never stop. The particle will escape the Earth's atmosphere. So then it says, well, all right, let's assume that it has got that velocity. It's going to escape. We're now going to find the time taken to rise to a height r above the Earth's surface. So in other words, when displacement is 2r. Remember the Earth's surface was r, we're going to rise to another r. Right, there was our formula, V squared, 2gr squared on r plus V squared minus 2gr. We've said capital V is root 2gr, which makes this much nicer, because if we sub that in now, we just get 2gr squared on r. That's v squared. So v is the square root. I've taken the positive square root because I know velocity is never going to be negative because it doesn't return. So velocity must be positive. So that's dr dt. Turn it upside down, I'll get dt dr. Separate the variables out. So we're going from r to 2r. Question is, what will the time end up being? So if I sub in 2r, 2r root 2r minus r root r. Now they've told us a specific thing we have to make it equal to. So let's play around with this. I can factorise r root r. That leaves me with 2 root 2 minus 1 times the root 2 here. Again, playing around with that. The r cancels with the r. No, that's still not what they want, is it? Oh, that is what they wanted. Okay, there we go. We got there eventually, playing with the surds. Oh, sorry.
I think, yeah.
All right. Oh, 3 questions. Yes, we got 3 periods.